Welcome everyone to a new episode. Today I'm talking to Nitin Jain about continuous variable quantum key distribution. Nitin holds a PhD from the Max Planck Institute for the Science of Light, and he's currently working as a researcher at DTU. Let's get started with the discussion. Nitin, thanks a lot for joining the session.
Thank you for the invitation, and yeah, it's a pleasure being here.
Mm-hmm. So we're going to focus on your paper, which is a paper on quantum key distribution. Just because this is the first interview we're doing when it comes to quantum key distribution, I think it would be useful for you to just quickly describe what the space is all about, if you would mind just summarizing that part of the field.
Yeah, sure. So quantum key distribution is, in a nutshell, a method to distribute random quantum correlations across a public communication channel, an insecure public communication channel, to two entities who are normally called Alice and Bob. That's a very typical cryptographic setting. And the communication channel is public, which means anyone and everyone is invited. And of course, we focus on an adversary or an eavesdropper who is normally called Eve. And the objective of quantum key distribution is to provide Alice and Bob with secret keys that can then be used for the purpose of encryption or some other cryptographic tasks. In this process, Eve, so this is like an information theory game. You have correlations between Alice and Bob. And if Eve tries to meddle during the communication, she will also get knowledge of the correlations, but it will result in a decrease of the correlations that Alice and Bob have. So roughly speaking, at the end of what is called a protocol, which is a sequence of steps that Alice and Bob need to conduct, they will have some correlations between themselves, and they can estimate what part does Eve know, and from there on they can decide whether the channel is safe, as in if they have a sufficient length of the secret key that can be used for whatever cryptographic task they want to do, or they can decide to abort this QKD protocol and try later. The main thing to know here is that the message that they wanted to share, that remains confidential. That is not sent out on the channel, and that is not eavesdropped by this adversary. And this eavesdrop detection capability is very unique to quantum key distribution. So that's not possible in classical cryptography. Mm-hmm. And then the other thing is
So maybe to just also bridge the gap between classical cryptography and quantum key distribution, what's the reason for the introduction of these quantum algorithms on the scene, let's say? So we already have traditional cryptography algorithms. Could you just summarize why these quantum algorithms are now being investigated and what the reason is for sort of trying to push those across the line?
Yes, so if you say the word quantum algorithm, I think of quantum computing, and that's a different subfield of quantum information science and technology. Quantum cryptography uses what are called security proofs, which are obviously like some mathematical frameworks where Alice and Bob can compute what correlations they have, what correlations Eve has during this process of quantum key distribution, but they don't use a quantum algorithm like, for example, Shor's algorithm. They do use properties or they use the laws of quantum mechanics, so fundamental principles such as Heisenberg's uncertainty principle, the no cloning theorem. So these bedrocks of quantum mechanics, of course, are fundamental to the security provided by quantum cryptography.
Mm-hmm. What I was aiming for a little bit with that question was the robustness against other quantum computers on the scene. So my understanding, and please correct me if I'm wrong here, is that these quantum key distribution, I don't know whether to call them algorithms or procedures or whatever we would group that under.
Protocols, I think, is the most common word used.
Okay. And my understanding is they are more robust to, let's say, the advent of quantum computers on the scene in general.
Yes.
Even though they don't rely on quantum algorithms necessarily.
That's very true. So what quantum key distribution is enabling is like Alice and Bob obtain some common bit strings, and these bit strings can be used as one-time pads, and that gives you an information theoretically secure cryptographic framework. The problem with one-time pad is the length of the one-time pad needs to be as long as the message you want to encrypt. So if it's just like a text message or something like that, then it's okay. But if you want to encrypt a video stream, which is a few megabits per second, then you need your quantum key distribution system to also be able to generate keys at such a rate. And this is a big challenge. Apart from that, one-time pad also has some other weaknesses. It is information theoretically secure, no doubt about it, but in practice, it's insecure because of, for example, what is known as the malleability of one-time pad. So what people normally use is some other symmetric encryption key protocol, and let's say the workhorse here is called the Advanced Encryption Standard, or AES. For this, you need a 256-bit long key, and you can use this key for encrypting like a few gigabytes of message in one go. And then a few minutes later, you can use new keys, again 256-bits long, to encrypt yet another few gigabytes or even terabytes of message. So that's what is typically used. And against advanced encryption standard, if you use a quantum computer to break the security, you get what is called a quadratic advantage. And this is in stark contrast to so-called asymmetric cryptographic algorithms, which is what our cryptographic infrastructure uses today. So this is also called public key crypto systems, and the typical cryptographic algorithm which is used here is RSA. So here, if you use quantum computers, you get an exponential advantage, and what that means is, with today's technology, if you use classical computing, you use like clusters and clusters of machines to break, let's say, RSA, which uses 1024 bits. You probably take a few years, but instead, if you had a quantum computer, you would be able to break the security in a few hours or maybe a day. So that's what I mean by exponential advantage. Going back to AES, like Advanced Encryption Standard, which is a symmetric key protocol, there the quadratic advantage would mean instead of 100 years, it takes maybe 10 years or 20 years. So AES is therefore computationally secure, because the kind of data, the kind of confidentiality you want, you are fine if this stays intact for a few years. Of course, it depends on the kind of data. So if you have military secrets or some financial data, that maybe has a lifetime of tens or like 50 years or so. But if your horizon is just a few years, then AES is perfectly fine. It's not vulnerable to quantum computers. So that is the bottom line.
So two questions as a follow-up to that. The first one would be, when we talk about exponential or polynomial advantage, comparing quantum cryptographic, or well, quantum computer systems trying to break essentially these cryptographic protocols. we are referring to time complexity with respect to the number of bits used in encryption. Is that the correct way of thinking about it?
Yes.
Okay. The second follow-up question I would have.
Sorry, that's still not. It's partly true. So what it does not imply is if I'm using AES with 256 bit, and if I suddenly jump to 512 bits, it's not obvious that you will get a polynomial advantage. But with respect to the asymmetric key cryptography, like RSA or Diffie-Hellman, so problems based on discrete logarithms or prime number factorization, there it is more or less true. Like you can go to 2048, which I think is the state of the art right now. So you can increase this size and then get some bit of an advantage against a quantum computer. But yeah, exponentially speaking, there's not a lot that you gain.
Mm-hmm. Okay, last introductory question I would have is just for context. Do you know why these asymmetric cryptography protocols are currently being used as opposed to the symmetric ones in general? Given that the symmetric one seems to be more robust for quantum computers or against quantum computers, I'm sure that's not the only consideration, but just from the narrow perspective that we're looking at now, it would seem like the symmetrical ones are actually more robust.
Yes. So I think the underlying problem is that of key distribution. So you have two parties that are separated, they have a communication channel. How do they obtain these symmetric keys in the first place? With quantum key distribution, which a better way of calling that is quantum key growing, what you also need is some kind of a pre-shared secret. It can be like a password. So you and I have like a common password. From that, we can grow this to more secret keys that can be then used for encryption. But we need to start with some kind of pre-shared secret, because if we don't have that, then the only way we can do a cryptographic task is through asymmetric cryptography, where the principle is I have a pair of keys, you have a pair of keys, which are called public and private. So if I want to send you something, I will use your public key to encrypt it, and then you will use your private key to decrypt it. This is computationally insecure, but that's how the field developed from 1970s onwards, and yeah, as of today, public key algorithms are what rule the cryptographic world. But yeah, I think this is the main issue, that you cannot distribute symmetric keys. Then, of course, encryption is not the only cryptographic task. Authentication is another, and their symmetric key algorithms usually don't have much of an advantage.
Yeah. And there, I suppose we're talking specifically about classical cryptography algorithms, so that you would need to have a pre-shared secret in advance specifically for those, or are we also talking about quantum key distribution here, that you would grow your key, or I'm not sure exactly what term you referred to there.
Okay, so if we use asymmetric key algorithms, we don't need to have any kind of pre-shared secret. We can just use each other public keys, which, as the name suggests, are publicly available, so anyone can access them. But the only way you can then do the decryption is when you use the private key, which, again, as the name suggests, is private to you or private to me. So this is something which is not known to anyone else. And this is, of course, quite a remarkable way, because, I mean, cryptography, the history of cryptography goes down to like several thousands of years, but several hundreds of years. But this idea of asymmetric cryptography was born only like a century ago. So yeah, that's the advantage, where like if two or more entities have never met each other and they want to do some cryptographic tasks, they don't need to have a pre-shared secret. In case of quantum key distribution, the reason for having a pre-shared secret is that's because of an attack called man-in-the-middle attack, which is as simple as Alice and Bob are communicating, but Eve comes, she cuts the line in the middle. To Alice, she will appear as Bob, and to Bob, she will appear as Alice. So the only way Alice and Bob can prevent such an attack is by authenticating each other. So they know that if Alice receives an encrypted message or whatever, she knows it came from Bob. Mm-hmm. And vice versa, Bob needs to be sure that the message that he got came from Alice. Mm-hmm. And this is only possible if they start with some kind of pre-shared secret. And that's a task that quantum key distribution does not solve.
Mm-hmm. Just very quickly, do you know what the ambition is in order to solve that problem? Is there an intention for how we can get around that? Let's say quantum key distribution would be widely used, some years from now. For this pre-shared authentication / secret, do you know what the ambition is for how that would be handled?
Yeah, that's a fantastic question, I think. So in the literature, most people refer to using, in the beginning, some asymmetric algorithm, but let's say with a really, really large key size, so that they can give an assurance that even if there is a quantum computer, it will not be able to break this in time. And by the time this has been done, the asymmetric part of the cryptographic algorithm is already over, and Alice and Bob have already obtained a pre-shared secret from which they have started growing their quantum keys. And at that point, if an adversary tries to break the security of the protocol, then he or she would be limited by the laws of quantum mechanics, at least in principle. But otherwise, this definitely is a limitation of quantum key distribution. In cases where a pre-shared secret is possible, so just imagine an organization that has 2 data centers. So they can just place their trusted devices with this pre-shared secret or a password, and then they start to grow keys. So that's entirely a feasible situation in which quantum key distribution would be able to work.
Okay, thanks a lot for that explanation. So maybe we can dive into the actual topic of this talk, which is one of your recent papers, so practical continuous variable quantum key distribution with composable security. As an introduction to that, would you mind summarizing just what the ambition for that particular paper was?
Yes. So I think the key word to explain right now is composability, which is it's a notion of security that allows modular design of a cryptographic systems. Put in another way, if there are 2 cryptographic tasks that are known to be secure as a standalone, will the resulting system be also secure? This is not a trivial question to answer, and you can take one approach, which is you simply examine the security of this entire composed system in a standalone manner again. But apart from being tedious, this is also prone to errors. So a better approach is to come up with security definitions for your individual cryptographic tasks in such a way that when you combine them, you can give a security assurance in a quantitative way. The best way of explaining this is by coming up with this term, which is the maximum failure probability. So you have a cryptographic task. Let's say you calculate the maximum failure probability, which means, and let's say this number is 10 power minus 3. What that means is this cryptographic task is going to provide you security that you need, except with a probability of 10 power minus 3. Then you have another task with another such failure probability, and what the composability framework allows you to do is you simply have to add these two probabilities, and this is the maximum failure probability of the resulting system. So this is a completely classical cryptographic primitive or classical cryptographic mechanism, and I believe it was in the early 2000s that people came up with this paradigm. What we have done is explore quantum cryptography in the context of quantum key distribution, or more specifically continuous variable quantum key distribution. So as of today, there are two main flavors of QKD, quantum key distribution. The more famous one is discrete variable, where the main difference is that when you code information in your quantum states, then there's just a discrete number of degrees of freedom that are used for encoding information and decoding information. Whereas in the continuous variable case, you use some properties that ideally can be any value from minus infinity to plus infinity. So they are continuously valued. So coming back to the paper, our objective was to show an experiment using a continuous variable quantum key distribution system that is able to generate keys which assure composability against a class of attacks called collective attacks. I can elaborate on this. So essentially, the QKD protocol has a quantum stage and a classical stage. So after the quantum stage is done, which is essentially preparing quantum states, sending them over this insecure public communication channel over to the other party, which is so it's a transmitter receiver kind of communication system, and then the receiver does a quantum measurement on the states and gets some measurement outcomes.
Sorry to interrupt, but just to make it clear, I'm sharing the screen now as well. I'm guessing you're referring to the figure that I'm sharing here. So just for the final presentation, you can refer to this one as well. So what we're talking about right now is the top section of this figure, correct?
Exactly, yes. So this is done over a quantum channel, and after this, your quantum stage of the protocol is finished. Then you start with the classical stage, which again has these different steps. And at the end of this, or maybe to go over these steps, first you need to make sure that all sources of errors that may have happened are removed, and this is performed by something called information reconciliation. Then the next step is to estimate the parameters of the channel. The objective of that is to find out what degree of correlations the eavesdropper may have obtained while you were doing the communication over the quantum channel. And depending on the outcomes of this parameter estimation module, you can then say, okay, it is possible to generate a key of a specific length, or the quantum channel is unsafe, the amount of eavesdropping was too much, so we cannot generate a key. So if that's not the case, if you can generate a key, then you perform the last step, which is called privacy amplification, which is because Eve still has some partial knowledge of whatever of the quantum states that were prepared and measured. So you need to make sure that this information that Eve has goes down to a negligible value, and that's basically the objective of this privacy amplification module. And at the end of this, you generate secret keys which are identical for Alice and Bob. So that satisfies the property of correctness. If and the fact that you were able to generate the keys themselves shows that your QKD protocol is robust. So if there was absolutely no interference from Eve, then you would definitely generate keys. But if Eve has meddled, you still are able to obtain shorter keys. So that's basically implying that your QKD protocol is robust. And finally, the fact that these secret keys are random, because if they were not random, then Eve can predict what these keys are. So you need like as I had introduced QKD, it's a method to distribute random quantum correlations. So the fact that your keys are random then allows you to say that the protocol is secret. So these three properties, secrecy, correctness, and robustness, once you have satisfied them, then you can say that your protocol is composable, or the keys that are generated satisfy the notion of composability.
Okay, a number of follow-ups on that, but perhaps the first one would be, given that when we have partial interference on the channel, we would limit the size of this key. Is there a reason why you would not go above and beyond in terms of the key size, so that that would not be an issue, provided that the eavesdropper does not have, let's say, complete interference of the channel? Are there primarily time restraints here that you need to adhere to, or is there another sort of factor keeping this on a limited key length?
Yeah, so the limitations to the key length come. There are several reasons. One is, of course, the information that the eavesdropper has, but apart from that, you also make a lot of assumptions on how your QKD hardware is performing. And in the end, if you want to give a security assurance, then you need to take into account all these imperfections, all these assumptions that you have made. So, for example, the simplest way in which people calculate key lengths is assuming that Alice and Bob have exchanged infinite number of signals, which is not possible in practice. But this allows you to obtain what is called an asymptotic key estimate. However, when you come down to the fact that you actually exchange only a finite number of signals, let's say 1 billion or 10 billion or 100 billion, then you need to make sure that when you do the parameter estimation, you take into account the statistics. You may have been unlucky, and in the 10 per 9th signals that you exchanged, Eve's interference could not be properly captured. But the reality is that Eve has actually meddled more than you have estimated. So you need to calculate some kind of worst case estimates. So this is again a penalty that goes in reducing your final secret key length. And these are all the limitations that eventually go and reduce your key length, but at least provide you with a certain assurance. So like this maximum failure probability of the entire QKD protocol. So of course you can try to increase the key length by having hardware which is faster. So instead of exchanging 1 billion, it's able to exchange 100 billion signals. But there you again have issues such as stability. In the end, you have to estimate certain parameters, and if you capture 100 billion signals, then the amount of fluctuations that you have will be higher, like generally speaking, than if you had captured 1 billion. So then again, when you subtract the worst case estimates, you may actually end up with a key length which is or a key fraction which is lower.
Mm-hmm.
So this is related to the stability of your hardware. You need to make sure that your quantum key distribution system is robust, it's stable over the time frame where you are doing your quantum key exchange and then the resulting classical process.
Okay, great. So then just to wrap up the initial figure here, we would then have a authentication process that sort of lives outside of this quantum key distribution that's already done. And then this quantum channel would be the one providing the necessary information to build up, let's say, a preliminary key. And once you essentially ensure that you don't have any interference or significant interference on this channel, you would apply the hash function, and I guess that would be done separately for both individuals. So Alice and Bob would apply it themselves. There would not be, let's say, a application on one side and then a transmitting of the updated key, but rather they would apply it individually, and then once you've done that, you have two identical private keys that you can use to essentially, communicate through the secure channel.
Yes, so that's correct. Maybe just one remark is, so Alice and Bob have, let's say, a repository of hash tables or hash functions, and as shown in the figure, Alice will send a seed which allows them to choose the same hash function, because everything before applying their function is the same, so they need to apply the same hash function in order to generate identical keys. Yeah.
Okay, so you mentioned before that these kinds of architectures, when it comes to the composability attribute, are subject to collective attacks in particular if they don't display the composability attribute. Now, is that the only attack that they're subject to, or are they also subject to other kinds of attacks if they don't display that attribute?
Yes. So when collective attacks are a class of attacks, and these are basically assumptions that you make on how powerful your eavesdropper is. So most generally you would say the eavesdropper is only limited by quantum mechanics, and in that case you get what are called general attacks or coherent attacks. So in terms of what Eve can do is, whatever is being sent on the quantum channel, she can simply do some quantum process on it, store the outcome of that in a quantum memory, and then send something to Bob. And then after Alice and Bob have done all the classical processing, she can do some classical processing on whatever she had stored in a quantum memory. So this would be, so Eve is allowed to do anything, like she can, her actions are completely arbitrary. It turns out that to prove security in this case, your worst case estimates become really, really bad. So we were not able to prove security against general attacks in this paper. But collective attacks are where you restrict Eve to only a certain number of operations which are IID, so identical and independent and identically distributed operations. And so this attack category is, let's say, reasonable. You can, of course, be even less paranoid and allow only more restricted attacks, which are called individual attacks. In those attacks, Eve is allowed to process only one signal at a time. So there, obviously, you will get a key length which is higher, but then the security assurance is lower. In case of collective attacks, your key length, your final key length will be lower, but you can you are guaranteeing the secrecy against collective attacks, and so on for the general or coherent attacks, where in our case we did not obtain a key, but had we, then the security assurance would have been the strongest possible.
Okay. One topic I would want to get into is you're displaying composability, which is sort of the main, I guess, takeaway from the paper, that you were able to ensure that with this continuous variable encryption. Can you perhaps summarize what you did, if that's possible in a brief way, to ensure composability, and maybe put that into context of some of the previous work that's been done in the similar space? Like, what is different about the architecture we're looking at now compared to previous attempts that makes it so that it fulfills this property?
Yes, I'll try. So I had mentioned discrete variable and continuous variable, and discrete variable QKD is certainly more advanced, and there have been number of implementations where composability was proven in proof of concept experiments. In case of CVQKD, there are different ways in which the quantum stage can be implemented. One of them uses so-called entangled states, which are not very easy to produce in the lab, but they allow for a certain kind of security analysis where composability could be achieved. So this experiment was done around 7 or 8 years ago, but the problem was that your key fraction calculations were very conservative, and as soon as you went to quantum channels of higher loss, so your public communication channel is usually an optical channel, and this has loss, and the more loss you have, the length of your key also comes down. So this particular demonstration with entangled states was able to report a key generation over very small channel lengths. There is another way of doing CVQKD, and that is using what are called coherent states, which are very simple to understand. You just take the output of a laser and you attenuate it. You make it dim so that on average you have just one photon, and that gives you a coherent state. So this, of course, is much easier to produce, especially because things like these have been done in classical optical telecommunications for quite some time. So our aim was to show composability using coherent states in a CVQKD system. So this was, let's say, the experimental side. Now on the theoretical front, you need to calculate all these worst case estimates and confidence intervals that I mentioned. And until 2015, there was no security proof, like there was no mathematical framework where composable secret key analysis was possible using coherent states. Finally, in 2015, there was a theoretical proof, but apart from being rather complex, the worst case estimates that you got from this proof were also pretty high. So in the end, this was again a bottleneck. So we collaborated with some theoretical groups who came up with a much smarter way of calculating these confidence intervals, which led down to a massive decrease in the penalties that basically reduce your final secret key length. This in a nutshell was how our theoretical security proof was reasonable enough to give us some finite non-zero secret key lengths. And on the experimental side, of course, I mentioned that you need your system to be very stable. It should be able to produce and acquire as many signals as possible in as short time as possible. So this was, let's say, another experimental challenge that we were able to solve, and finally obtain keys that had this assurance of composability.
Okay, great. I figured that for the last few minutes we could also look at the experimental setup for this protocol. So I'm sharing that now on the screen here, and I figured we could have a look at this. I think specifically it would be easiest maybe to start with the central segment, but just to wrap this up or to summarize what we see in the figure, we have the transmitter side, that would be either Alice or Bob, and then the receiver, which would be the other participant. And then in between here we have the fiber channel that this information would be passed through, and then also, this quantum random number generator and some form of computer here. If we describe or talk about this setup briefly, and perhaps starting with this quantum random number generator, what is the purpose of having this one? Is that to ensure that the keys are random, as we talked about before, or is there another purpose?
Exactly, yes. Quantum random number generator, as the name suggests, produces a sequence of random numbers, and those random numbers are used for producing signals which are modulated in the transmitter and then transmitted on the quantum channel to the receiver, who performs a kind of coherent detection to get so the transmitter is encoding these random values and the receiver is decoding these values. Of course, there's some intrinsic noise, some fundamental noise, which is also needed to ensure the security of continuous variable quantum key distribution. But in the end, yes, that's the role the quantum random number generator is playing.
Okay, maybe a naive question, but we have two inputs to this computer illustration here, one of them being this ADC input spectrum. What is the reason for using this spectrum when we then create this AWG output spectrum? Like, what's the reason for not just having sort of the random number generator?
That's perhaps not so well explained. So maybe I can just quickly go through the procedure. So we start with these random number generator, random numbers, and then we use a certain kind of modulator, an optical modulator called IQ modulator, and the random numbers are used to create an analog waveform, a radio frequency waveform, which is applied using an arbitrary waveform generator, that's AWG, onto this IQ modulator. So that is how you are encoding information about the key in an optical sense. So the output of the laser goes through the IQ modulator, and the IQ modulator also has these radio frequency inputs. And then you use this variable attenuator, VATT, to bring down your coherent state amplitude to a level that allows you to do continuous variable QKD. Then it gets transmitted on the 20 kilometer channel and inside the receiver you perform this coherent detection, and what is shown here is the input spectrum, so like frequency information of the signal which is captured by an analog to digital converter in the receiver, and at the transmitter you have the frequency information of the signal which is sent to the arbitrary waveform generator. So in sense of what came first, it's the AWG output spectrum, and later comes the ADC input spectrum. But this is again just to visualize what is going on. The quantum data, like which is this broadband sort of structure in the red, like the red trace, you can see in the ADC input spectrum. This is where our actual quantum signals, like the random quantum signals, reside. Now, in order to be able to communicate the transmitter and receiver also need to perform a lot of other functions. They need to, for example, be synchronized, and that's not possible to do just with quantum data because this is very weak. So we use what are called pilot tones, which you can see both in the AWG output spectrum and the ADC input spectrum. So with the help of these pilot tones, you are able to do the tasks of synchronization and also something called phase and frequency compensation. So once you are done, then you can decode the information that was sent by the transmitter to the receiver.
Mm-hmm. Okay. If we focus also on the RX laser here for a second. So I think this one, the transmitter laser is quite clear that we need that one. But what is the purpose of the receiving laser on this side? How come we cannot just interpret the signal as it sort of comes through this fiber channel? But why do we need a laser on the actual receiver as well?
Yes, that's a very good question. So if you go in, so I mentioned this discrete variable quantum key distribution system, and that's sort of the system you are visualizing, where you prepare a certain state and you at the transmitter send it, and then at the receiver you detect this state. This continuous variable QKD is a coherent technology, so you need a certain reference, or more appropriately a phase reference, in order to make sense of any of the quantum measurement which is done at the receiver. So when this field came into inception around 17-18 years ago, people used to send both their signal and a reference which was called local oscillator. So this was multiplex in a certain way onto the channel, and then at the receiver you would demultiplex them, and then you would use the reference to get information about your signal. But this kind of system, which is called a transmitted local oscillator system, because the local oscillator is being transmitted on the quantum channel, introduced some vulnerabilities. In order to get rid of these vulnerabilities, the new design, which has a local oscillator, because the source of your reference is now inside the receiver, you use another receiver laser. So this acts as a reference. Of course, this brings in certain challenges, and that is one of the reason you need all these pilot tones, etc., for the purpose of phase recovery. But that is essentially the answer to your question.
Okay, great. I see that we're starting to roll up on time, but I also want to check with you before we close. Given the results that you have in this paper, what would you say are sort of the next steps for this field, particularly if we're talking about CVQKD? Like, where do you see the field going now? What would you say are the obvious next steps to try and take?
Yes, so composability is about composing, let's say, this CVQKD system inside a larger application, which would be data encryption. Here what we have shown is just a proof of concept experiment where we say that we generated composable keys, but the obvious next step would be to show a deployment where these keys are fed into some kind of an encryption device which performs the actual data encryption. So this is something we are already exploring. Then another step is to try and prove security against composable security against general attacks. This is quite tough, but it's certainly another option we can take. Yet another step is, this was not so clear, but right now the key generation process happens offline. So we do the exchange on the quantum channel, then we store the results, and then there's digital signal processing that goes onto the receiver, and this is quite slow. So another challenge to solve is to make it real time or near real time. So these, I would say, are let's say the closest and most relevant steps that can be taken as an outlook to the current work.
Just one consideration on the first point you mentioned. So putting this together into a production system, let's say, has that been done successfully on systems that don't display composability, or is this something that's generally a new topic for the entire field of QKD?
This has certainly been done. There are several startups and companies across Europe and also in Japan or Australia or United States who are building such quantum key distribution systems and deploying them in test beds. So they generate keys, they encrypt. Yes, composability, I believe, at least I'm not aware of any commercial entity that claims that they use a composable security analysis and then they can assure that the larger application inside which their QKD system resides can then assure composable security. But we are definitely exploring this. We actually have basically rack compatible devices. So the setup that you are seeing right now was on a large optical bench, but over the last 2 to 3 years we have been working on putting them inside a portable box which looks like your computer workstation, and we have also shown deployments already in the field. We had a demonstration together with Danske Bank, which is one of the largest Scandinavian banks, and we also had another demonstration with an energy distributor. So yeah, this has definitely been done, and in the coming years I'm sure there will be a lot more demonstrations which will also include composability.
Perfect. I think that's a good place to break. I would just thank you very much for taking the time. I enjoyed the discussion and appreciate you joining me.
Yeah, thank you so much, Niklas.